Assalamu alaikum. How are you, my dear students? Hope you will be fine and okay. I welcome you all into my today lecture. So let us start with the name of Allah Almighty. Our today topic is the photoelectric effect. Let me explain to you that in our previous lecture we talk about the black body radiation, the black body radiation, the black body radiation. In the black body radiation, there we explain the black body radiation on the quantum, on the basis of the quantum model, and we came to the conclusion that the black body radiation is in fact not happening in continuous manner, rather it occurs in discrete manner. That is, the energy emitted is in the form of energy packet rather than continuous energy. That is what we have learned in the previous topic. There is also in the previous classes you have also learned about the thermionic emission. Thermionic emission. That is the process when of the that is the process in which a metal surface when heated emit electrons. That was the process of the thermionic emission, and then you came to know that this occurs because in the metal surface the free electrons which are bound to the atoms with very less energy, when get energy from certain external sources, their kinetic energy increases, and then they are capable of leaving the metal surface. In a similar way, we have also one such kind of effect known as the photoelectric effect, but here the situation is different. Here we do not use the heat energy. Here the light is doing this for us. But let me first, right in the beginning, I want to tell you that the photoelectric effect is, I'm sorry for the interruption. So I was talking to you about the that is that one of the most important result of the photoelectric effect, which I want to tell you right in the beginning, that it is in fact the the it is the experimental verification, the experimental verification, it is the experimental verification of the, it is the experimental verification of the particle nature of light, particle nature of light. If you remember your class 10, there you studied very briefly that light has dual nature, both wave as well as a particle. So here the photoelectric effect is one of the first experimental verification which suggests that light can behave as particle, and later on I will explain this to you. Now what in fact this process is. Photoelectric effect is the process, it is the process of, it is the process of, it is the process of the ejection, the process of the ejection of electrons, electrons from, electrons from the metal surface, electrons from the metal surface, the electrons from the metal surface when light, not all sort of light, when light of a particular frequency. And inshallah later on I will tell what that particular really mean? When a light of a particular frequency shines on it, shines on it is called the, this process is called the photoelectric effect. Whereas the emitted electrons, the emitted electrons, the emitted electrons are called the photoelectrons, the photoelectrons, and the current caused by it, and the current caused by it is called the photoelectric current. The photoelectric current, the current caused by it is called the photoelectric current. Now, the experimental arrangement for this, the apparatus, which kind of apparatus is used for this? Here, let me explain this to you. In this diagram, here you see the experimental arrangement. Here we have the evacuated glass jar, as you see here. This is the glass jar or tube. This is the glass tube, evacuated glass tube. That is almost all the air is removed inside it. That is the, you can say that it is at very low pressure here. Now you see that they there are, that is inside the it are two electrodes. Here we call one electrode is this, the one which you see here is, look, this is what we call the cathode, and this is what we call the anode. And you see here that the, this is anode and this is the cathode. You see here the anode is connected with the negative terminal of the potential difference here, while the cathode is connected with the positive terminal of the battery here. Now you see the ammeter here. The ammeter will indicate any sign of current exists here. The voltmeter will tell us about the, it will tell us about the potential difference. Now there is that in complete, when you place the apparatus in a complete darkness, then what happens, that is, look, right in the beginning, as you see here, that look, there is just no connection between the two metal plates. And of course, when you connect them across the battery in the absence of the light source, the galvanometer will indicate you zero right in the beginning. Or when the apparatus is placed in darkness, then it will show no current. Now strange thing happens, as you see here. Look, that is that when the apparatus is exposed to light, as you see here, right, when light of a particular frequency, right, as you see, we are having here the adjustment of the frequency, the various frequency you see. Each color of light indicates a different frequency. Look, this is blue and then the purple, like that. Now this does not happen at all frequency, it only happens at a particular frequency here. Now what is going to happen here, that when you allow the light to fall on the metal surface, the emitter indicates you current, right? That is the indication of the current shows that there is definitely the there might be definitely electrons present in the region between the two plates. That may be the cause of the current. Now the question is that where are these electrons comes from? These electrons comes from that when the light shines on the metal surface, it ejects the electron from the metal surface, and that become the cause of that electric current, which we call the photoelectric current. And that photoelectric current we actually denote by the, if we just take it a conventional current, then we denote it by IP, the current due to the photoelectrons. Right now we will study various effects, the effect of the intensity of light on the photoelectric current, the effect of the frequency of light on the photoelectric current, and on the stopping potential. So we will discuss the various cases here right now. Okay, this is one of the most important effect which cannot be explained on the basis of the classical mechanics, or the classical mechanics fail to explain this effect. I will revisit this equation when I explain to you the summary here, the summary of the topic. Let us move on forward. First of all, I just want to explain to you the to explain to you the intensity effect of the light, right? That is, let us see here first the intensity versus electric current. Now you see that, look, if we increase the intensity of light, increasing the intensity of light, increasing, yeah, using light of various intensity, using light of various intensity, right? Here you see that we have the intensity of light, look, that is the, it is in such a way that intensity I1 is smaller than intensity I2, which is smaller than I3. Now look here, going back to the previous equation, to the going back to the start here, as you see, look, now if we increase the intensity of the light here, then what happens, the photoelectric current increases and increasing. Now if we disconnect it, and if we just connect the cathode this with the negative terminal of, with the positive terminal of the battery, and making this in the next arrangement, for example, if we make this if we connect the cathode with the negative terminal of the battery, like this with the negative terminal of the battery, and the anode with the sorry, and the anode, the, if we connect the cathode with the positive terminal of the battery, and the anode with the negative terminal of the battery, then what happens, then you will see that the current decreases if you increase the reverse potential. This is what we call the reverse potential difference. If we increase the reverse potential, then a stage will reach that there will be no current, and the galvanometer will indicate zero, even though there will be a higher reverse potential difference. Why? Because you know that when the electrons are being emitted, so you have now made the anode negative with respect to the cathode, and the cathode you made positive with respect to the anode. So the electron being emitted are, the electrons are not being allowed to travel. Why? Because this is now become the negative plate, and this negative plate will repel the electrons back, right? So this is one of the reason that only few electron will make its way, and those electron will have a very high kinetic energy. But if you increase the reverse potential, a stage will reach that that the a stage will reach that no electron will make its way towards the positive, towards the anode, right? So now to explain this here, we call this, that is, we call this about potential as the stopping potential. So what is stopping potential here? The stopping potential, stopping potential is the reverse potential difference, reverse, the reverse potential difference for which the reverse potential difference for which the photoelectric current falls to zero. The potential difference, the reverse potential difference, the reverse potential difference for which the photoelectric current falls to zero. The photoelectric current falls to zero. That is, this becomes zero. Now here, look, in this graph, as I told, the intensity versus this graph, this is the stopping potential, the reverse potential, this is the photoelectric current, and I will denote the photoelectric current by IP. Now you see that, look, if you increase the intensity of light, the photoelectric current increases. The photoelectric current increases, as you see here. The photoelectric current increases, but it has no effect on the stopping potential. The higher the intensity of the light, there will be only a higher photoelectric effect, the photoelectric current, but the stopping potential is still remain the same. Now there is, look, the classical mechanics, if we just write the prediction for this in the classical, according to the classical physics point of view, and one, this is what the classical physics point of view, and this is what the experimental result, here, what the classical physics predict and what the experimental physics predict. The dependence on light intensity, I will label it as dependence on light intensity. Dependence on light intensity. This is the first point here. Now, according to the classical physics, predicts that the electron should absorb energy continuously from EM waves. Electrons should absorb energy continuously from the electromagnetic waves, yeah, from the EM waves, yeah, from the light waves. The kinetic energy of the ejected electron, then the kinetic energy of the ejected electron, should increase. The kinetic energy of the ejected electron should increase. It should increase, but it is not the case. What the experiment reveal, as you see here, the experimental verification here, what you see here, this tells you that the maximum kinetic energy is independent of the intensity of light. Maximum kinetic energy maximum kinetic energy, maximum kinetic energy of the emitted electron, is independent, is independent of the intensity of light, of the intensity of light. And the classical physics fails to explain this. Now you see here why. Because you know that the maximum kinetic energy of the electron, mv square max, this is directly proportional to the stopping potential, electron volt, right? And this equation I did it to you many times since from the start of our uh, lectures, right? That the maximum kinetic energy is equal to this. So you see that, look, if we increase the intensity of the light, then the kinetic energy should increase. But here you see that for the various intensity, what you see here, that you see that the stopping potential is the same, right? That whatsoever that the intensity, increasing the intensity, the very shortcut, increasing intensity, increasing intensity of light does not increase the kinetic energy of the emitted electron. And this is very strange. Classical physics says it should, but this is not happening here. And this is why that what we see here, look, that we see that the stopping potential is the same. So now, but what in return, what does it shows? It only shows that increase in intensity only cause increase in the photoelectric current, in the photoelectric current. Okay, and then later on I will explain this point to you why, and that could only be explained by the quantum mechanical nature. Clear? Now another important relationship here which you would like to see here, that is that now another important feature for this which I want to explain to you is the dependence on what, that the dependence, the dependence of, that is the dependence of on the stopping potential is in the case of before, of the stopping potential on the frequency of light, on the frequency of light. Okay, and in this situation here, what we see here, that look, there is another graph, and this graph is right here. Here you see that we have what, we have the various frequencies. This is what I would like to label as the frequency f1, frequency f2, and frequency f3. Here in this case, the frequency f1 is less than f2, is less than f3. And what result you see here? This is the photocurrent IP. Here you see that, look, that the photoelectric current is the photoelectric current, the photoelectric current is independent, is independent of the frequency of light. But another important point here which you see is this one, that stopping potential and hence the kinetic energy max is the function of what? Is the function of frequency. Is the function of frequency that of the emitted light, that it indeed depends on a frequency. So here you see that, look, that the experiment reveals, that experiment shows that if we increase the frequency of the light, that it does not increase the photoelectric current. The photoelectric current is almost the same for the same frequency here, but the stopping potential indeed varies. That a higher frequency need more stopping potential than light of lower frequency. So it means that the photon of higher frequency cause the emission of electron from the metal surface of having higher kinetic energy, while that is photon of low energy will only eject low kinetic energy electron from the metal surface. So this is in clear contradiction with that of the classical mechanics. The classical mechanics, in fact, it tells that the ejection at any incident light frequency ejection of what, and moreover, another important point here, which I will later on explain to you, and right, I want to explain it to you here. And if we just see the stopping potential versus the frequency, so here, yeah, you can say that the kinetic energy versus frequency relationship, kinetic energy or stopping potential, because kinetic energy depends on the stopping potential. So here you see that, look what happens here right now, that you see that the photoelectric effect, the photoelectric effect does not occur at all frequencies, at all frequency. It only occur at a particular frequency. So here you see, if you increase the frequency of light, there is no photoelectric effect. Why? Because the stopping potential is zero and there is no electrons emitted from the metal surface, no electron emitted from the metal surface, until at a particular frequency, this frequency F naught, which is called the cutoff frequency, cutoff frequency or threshold frequency. When the frequency is increased beyond this value, then you see that there is a linear relationship between the stopping potential and the frequency. That if you increase the frequency further, the stopping potential and hence the kinetic energy of the emitted electrons increases. So this point, that why it only happens at a particular frequency, the classical mechanics fail to explain this. So what I would like to tell you here is that the first point is that the ejection the ejection at any incident light, at any incident any incident light frequency, the the ejection of electrons, okay, photoelectrons, at any incident light frequency, at any incident light frequency must happen as as long as the intensity of light is high enough to do so, is high enough to do so. Now you see that, look, in this region here, look, in this region, that if you see that if you use a light, that is the process wouldn't initiate, process wouldn't start, the process wouldn't start even at the highest intensity of light use. Highest intensity, right? That whatsoever is the intensity, but if the frequency is below the cutoff or the threshold value, the photoelectric effect is not going to start. So here you see maximum energy, and in this frequency, as I told, that is this frequency is this frequency depends upon what? Depends upon the nature of the metal surface, the nature of the metal surface. It is different for different metal surface. Here you see, look, for potassium, sodium, zinc, tungsten, and potassium, the threshold frequency F is different, and the maximum kinetic energy is, you see, look, the maximum kinetic energy function, right? So they does not start at same frequency. It is the function of what? Yeah, it depends on the nature of the metal surface. So for potassium, for sodium, for zinc, so the same, if you keep the same stopping potential, for example 2 volt, like you see here, the maximum kinetic energy, for example, if this maximum kinetic energy is 2 electron volt, so this does not occur at the same frequency. For potassium, this is different than for the sodium, which you can see here. This is what I explained, this is what I explained, this is what I explained to you in the previous case. So now you see here, look, here that this tell us the experiment has a different story for us, that this only occurs, yeah, I will write that this only occurs, the photoelectric effect only occurs at cutoff frequency, at the frequency, called cutoff frequency, right? So which depends on the metal surface, depends on the metal surface, depends on what? Depends on the metal surface. Here, as I told, in this case, that on the ejection at any incident light frequency must happen as long as the intensity of light is high enough to do so. This was here regardless, the classical mechanics think it, the regardless of frequency. But experiment has a different result. Experiment tell us that it should be in a different way. Then there comes the Einstein explanation. Right now, Einstein explained this Einstein model. Einstein, sorry. Einstein model of the photoelectric effect. Photoelectric effect. How Einstein explained it? Einstein predicted that photon gives that, according to this model, photons give, in the previous lecture I told you in the Blake body radiation that photons are chargeless and massless particles. Photon gives all of its energy, photon gives all of its energy to a single electron in the metal, to a single electron, to a single electron in the metal, to a single electron in the metal. Therefore, 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 the absorption, therefore, the absorption of energy, therefore, the absorption of energy is not a continuous process, is not a continuous process, is not a continuous process, rather it occurs in the form of, in discrete form, in discrete form, not that is, and that is what we call, that is sorry, rather it occurs in discrete form. This is in the form of what? This is in the form of the energy packet. Refer to what? The form of what? Energy, in the form of energy packet, which he called quanta and later on called it the photon, which are chargeless and massless particle. So here I would like to explain this to you now on the basis of the Einstein explanation. Here you see when the light falls on the metal surface. So the light has, each light has energy h into f, Planck constant, like that. When it fall on the metal surface, what happens? That the energy, the photo, that is the electrons absorb energy from the electron in the metal surface absorb the energy, and they gain enough kinetic energy to escape the metal surface, right? So how this happens to here, the amount of energy required that remove the electron from the metal surface is called the work function. So here, that according to the Einstein mass energy relationship, let us see here again that look, if we have this, that previous experimental arrangement, if this is cathode C, if this is anode, now look, this is ammeter, this is connected with the positive terminal of the battery, this is with the negative terminal of the battery. For example, when light of particular wavelength shines on it, like this, for example, this is light. So according to the Einstein, when light of a particular frequency, when it shines on the metal surface, so you know that what happens, it ejects the electron from the metal surface, and the electrons are then travel. Electrons are ejected, and these electrons then travel from cathode towards anode with some kinetic energy of the electron, half mv naught square, like that. So now here you see that according to the Einstein, the energy of the emitted photon, total energy of the photon, emitted photon, it must go first to knock down the electron from the metal surface, right? That is the one to in the kinetic, it will, like the kinetic energy of the electron, increase the kinetic. First of all, let me write it like this. Some, that is, some of the energy must be given off, yeah, work done in removing the electron from the metal surface. Removing electron from metal surface, from metal surface, plus the kinetic energy of the emitted electron, emitted electron. So you know that this is the energy of the photon. We already denote this by HF. This is called the work function. the work function. And what is this work function? It is the minimum energy required by the electrons to knock down, by a photon to knock down electron from the metal surface plus kinetic energy of the emitted photon. So this HF into work function plus the kinetic energy of the emitted electron. Now here, for example, in order to calculate this work function, as I told, what is this work function? Work function is the minimum energy required by the photon required by the photon to knock down or to eject electrons from the metal surface, electrons from the metal surface. Now, how to calculate this work function? Now you see that the work function is equal to what? The energy of the photon, the total energy of the photon minus the kinetic energy of the emitted electron. And the kinetic energy of the emitted electron can be calculated from the stopping potential. So here this is very easy. How to calculate this work function? As we know that this process does not initiate at all frequency. If the frequency of the incident photon is equal to the frequency F naught, F naught is the cutoff frequency or threshold frequency. It is the frequency at which the photoelectric effect is initiated. That is the frequency at which the photoelectric effect starts. Then at that point, the kinetic energy of the electron becomes the kinetic energy max. Only those electron then starts to move on. Now, so this work function will be then equal to what that this will be equal to HF naught minus. Now you know that below any frequency, only that is below that frequency, below the frequency F naught, the kinetic energy, the maximum kinetic energy of the electron is zero. For example, look how we can calculate this. That look, the last electrons that can arrive will have a maximum kinetic energy for that higher stopping potential. Right here or here you can say, like this one. Okay, so the work function can be then calculated. This work function can be then calculated by like this: HF naught, where F naught is the threshold frequency, and this depends on the work function and is different for different metal surface. So the photoelectric effect equation is that HF is equal to psi, the pi, the work function, plus the kinetic energy max of the emitted electron. Okay, so this is the kinetic energy of the electron. So now you can calculate the kinetic energy of the electron also. That is the energy of the photon minus the work function. Now let us see here, going back. In this case, look why it does not depends, why the photo, that is look here in this case, as I told you earlier, that we have the frequency of light f1, f2, f3 equals f, all light with same frequency. For example, you have a red common light and a red laser beam. In this case, they will all have the same stopping potential but different kinetic energy, but different photoelectric current. Why? Because that if you increase the intensity of the light, increasing the intensity of light only increase what? Increasing the intensity of light, the intensity of light only increase the number of ejected electron, ejected electron, electrons, and hence the photoelectric current, and hence the photoelectric, the photoelectric current, but no increase in the stopping potential. Why? Because the stopping potential is the function of the frequency only. But here, look, as you see here, so no effect on the stopping potential, and only the photoelectric effect increases, because from the Max Planck equation, if you remember, I told that the kinetic, that the energy of the photon NHF, H Planck constant. So here you see, if you increase n, you only if you increase the intensity of light, means you only increase the number of photon. In one photon, one electron system, and so more electrons are being knocked down, and greater what, and greater the photoelectric effect. Why? Because photo current is directly proportional to the number of photons. And here the story is different for the stopping potential. Here when you increase frequency, for example, look, if you use red or blue light, so blue has greater frequency than the red light. So therefore, that if you keep the intensity the same here, I1, I2, I3 the same, but the frequency F1, F2, F3 greater than F2, greater than F3. So here you see the frequency increases and the kinetic energy required will be what? Greater. That what happens then? Look, when a photon of higher, very high energy, look, when a photon of very high energy arrive, that is, for example, let us see here that if you have the photon of very high energy, if it arrive, so some of the energy will be given to the metal surface to so that, yeah, and the electrons are being knocked down from it, and the rest of the energy will be then now greater in the case of a higher energy photon than in the case of lower energy photon, and the rest of the energy will goes to as the kinetic energy of the emitted electron. It will goes to the kinetic energy of the emitted electron, and therefore the emitted electron will have a greater kinetic energy. So this all tells you about the nature of the sorry, this all explain the particle nature of the light here. And let me, as I told in the beginning, that I will explain this to you. Now here, look, when the light arrives, when it falls on the metal surface, okay, then it can only be treated as particle. Why? Because that if it were to be treated as light, it would be reflected. So it is considered as what? As a particle. And the all of the photon, we call that a photon, and the photon transfer all of its energy to one electron, right? The photon absorbs into the electron. This is what I would like to say. The photon by itself disappear and give all of its energy to the electron, due to which the electron is being ejected from the metal surface. But here the situation is that when you see the particle aspects of the wave, then at that time the wave nature will be missing, right? And here during the photoelectric effect, you will only see the particle nature but not the wave nature, mean that light wouldn't reflect, rather it would all absorb, right? That into the metal surface, that the electrons from the metal surface will absorb all of that is will the electron in the metal surface will absorb all the energy from the incoming photon. The incoming photon will just disappear into what, and that energy will be transferred into what, into the electron, and as a result which the electron will eject the metal surface and will travel with some of the kinetic energy towards the anode. So this is all about the photoelectric effect. The photoelectric effect has numerous of applications in the electromechanical machineries, starting from the automatic doors to the to the starting from the as I told the what I was telling to you, starting from what from the automatic doors to the photo diodes and even further. So you will find it's hundreds of application in electronics, and you can study these by yourself. The application of the photoelectric effect, it can be in the like as I told in the automatic door opening, it can be used in the remote control devices, and it can be used in the burglar alarms. Like it can be used as a sensor. This is what I would like to tell you. So thank you very much for being here, and inshallah see you in the next lecture. So this is all for now.